All right, welcome everybody. In today's group meeting, we have the third seminar, the third and last seminar of the series of seminars that Richard Lopp is given on light and atoms and light matter interaction. And we're going to talk about a covariant formulation of QED. And well, Richard, the floor is yours.
All right, thank you. So yeah, this is the last rendition of our lecture seminar series. And this will be all about the covariant formulation and how we can put it into context and connection to the formulations that we discussed in the first and the second lecture. So last week and the week before. So let's start. So again, in the beginning, we want to motivate. So why are we at all interested in this this formulation in particular? As we will see, it is related to much more work than before. In order to then study it properly, we need to start with the classical formulation first, and then we can talk about quantization and the problems that arise through quantization. And once we have done this, in particular for free fields, we can then include matter, and this will allow us then eventually to combine this with our previous discussions about light matter interactions and if we treat atoms non-relativistically. So first of all, what did we do in the past two seminars? That was, first of all, we derived the minimal coupling Hamiltonian, in particular in very great detail for the Coulomb gauge. And then we found for how we can relate equivalent representations, in particular via canonical transformations. And then what we did, we showed that, oh, sorry, that should be the multipolar Hamiltonian. So we derived in the second week the multipolar Hamiltonian for the more canonical way or the more usual way of where we had a classical center of mass, and then the fully quantum picture where we had the quantum center of mass, and we showed the phenomenology that arises from there. Okay, so now we want to find a covariant formulation of QED. This goes beyond how we treated atom before. And a couple of issues that need to be addressed here are, first of all, and we will see that we include more degrees of freedom, and what are the effects of those degrees of freedom that we just added. In that context, we will need then to discuss constraints, how to find physical states in a larger Hilbert space, and here I will follow the book by Cohen Tanuji mostly. So first of all, why are we at all interested in the covariant formulation of QED or the interaction of light and matter? Well, first of all, we just considered low energy physics. We treated particles non-relativistically that comprise the atom. We, in order to have a very simple approach, we reduced the dynamical degrees of freedom to very minimal, and that allowed a very simple quantization scheme. But by doing so, we broke the manifest covariance of the electromagnetic field. And if we want to, however, study high particle velocities, if you want to study high frequency photons, if you want to include radiative corrections, what happens if you have vacuum polarization correction and so forth. And in the end, if you want to include renormalization in quantum field theory, then it would be best to study manifest covariant approach to our theory. And in order to understand it properly, of course, we have to start classical again. And so let's see what we need first. So again, we define the form for potential that comprises of the scalar potential U and the vector potential A. And what we impose then, what we require for our Lagrangian, in particular the free field Lagrangian without any matter for now, that is manifestly covariant. And in particular, that it has to have the canonical conjugate to U. If you remember, in our usual Lagrangian approach, we did not have the time derivative of U in our Lagrangian and therefore did not have a canonical conjugate to U. And so let us just propose that we found now this, this very suitable Lagrangian in the following covariant form. And then we see it has now also, in principle, a canonical conjugate to U. Let's first now see how does it compare to our usual approach. And that was that we just had the contraction of the field strength tensor, the electromagnetic field strength tensor, that's just defined by the 4 momentum and the 4 potential and its appropriate derivatives. And the first thing to note here is that this is not equivalent to the Lagrangian that I just proposed, so Lagrangian 1, that we will need for the canonical covariant formulation. To see this, we can first look at the Fermi Lagrangian, which is also a very common Lagrangian that people work with. And you can derive, or you can achieve the Fermi Lagrangian by adding this term, quadratic in the 4 divergence of A, to the standard Lagrangian. And then you find that the Fermi Lagrangian from the standard Lagrangian differs by 4 divergence. And so they're equivalent and yield the same equations of motions. However, secondly, you see that the Fermi Lagrangian is not equivalent to the standard Lagrangian that we worked with before, just because we cannot write it in a suitable form like a 4 divergence. And so it's not equivalent. So to see that explicitly, let's look at the Euler-Lagrange equations. So for that, we write the free field Lagrangian and the interaction Lagrangian, that is just the minimal coupling prescription, where we defined the 4 current with the charge density and the charge current. Now we can compare the equations of motions of both prescriptions. So first of all, for this Lagrangian 4, you find that the box, the D'Alembertian of A is proportional to the charge current, and the box of U is proportional to the charge density. Of course, this is not the same as before in our standard approach, where we had the gradient and the time derivative respectively acting on lambda, and lambda is the 4 divergence of the 4 potential. So the question is now, how can we make it equivalent? Under what conditions are both sets of Lagrangians equivalent in yielding the same equations of motions? And that is what is known as the Lorentz gauge, a condition that we have to impose. So you can see it's very simple to just say, if lambda is 0, then obviously these terms vanish and they are just the same equations of motions. So the question that arises then is this condition of lambda equal to 0 compatible with the equation of motions of our new Lagrangian that we will need for our covariant formulation? So to see that, we can see that the equation of motions imply that the D'Alembertian on lambda is equal to charge conservation, which is by very definition 0. And the only thing therefore we require for the Lorentz gauge condition is 2 things. First of all, that at a suitable initial time, let's call it t0, lambda is equal to 0, and that can always be imposed. Secondly, that the time derivative at the same time point is also 0. And in order to see if we can do this, we can show that by using the equation of motions, that the time derivative of lambda is nothing else than the Gauss law, and therefore it is also suitable for a particular time to impose this condition. And so we know now that it is possible to choose lambda equal to 0 so that also lambda will stay 0 for all times after an initial condition. And the only remaining gauge freedom after imposing lambda equal to 0 is associated with the scalar function f, such that the box on f is 0. And this is the remaining gauge degrees of freedom that we have in our theory. Now, we can, as usual, find our Hamiltonian for the vector potential. It is, as usual, the time derivative of A. And for the scalar potential, it is no longer 0, but here we have now the time derivative of U. And so what it means in the Lorentz gauge in Fourier space is that k dot A, the Fourier transform of A, is not equal to 0 as usual, but now in the covariant approach with the Lorentz condition, that it is equal to the Fourier transform of the canonical conjugate to the scalar potential. And then after Legendre transformation, we can write the Hamiltonian density in Fourier space in terms of these variables that we've just derived. And we see that we have an unusual sign difference between the degrees of freedom associated with the vector potential and the scalar potential. And the question that arises now is, does it imply unbounded negative energies in principle? So let's first look at normal variables that we are usually looking for if we are interested in quantization anyways. So we can define the standard normal variable associated with the vector potential. That's just the generalization of x and p. And now that we know that we had an inverted sign associated with the scalar potential, we also invert the sign here between the as, which is just our scalar potential u, or the first component of the 4 potential, and its canonical conjugate. And via this definition, one can show that our normal variables evolve according to this equation. And if we have external sources, we have this source term here, and if not, then we have just the free evolution, as we are used otherwise as well. So this is just a very convenient choice of sign that allows us to have a very nice prescription of how we put all these normal variables into one variable. So, and then we can do our expansion of the potentials in terms of the normal variables. In principle, they are of this form, which is then very suitable for quantization. Now, we did not explicitly impose the Lorentz gauge, and so in principle, we still have 4 independent degrees of freedom associated with the normal variables to the scalar field and the vector potential. It is more convenient, however, to choose the normal variables in terms of the longitudinal and perpendicular directions to the wave vector modes of the vector potential, just as we know from standard non-relativistic treatment of atoms and light. And the question that arises now after this expansion in terms of normal variables, do we have actually 4 kinds of photons? And you probably guess already the answer will be no, because that is not what we know from our standard treatment. But how do we get there? First of all, let us impose the Lorentz condition that tells us that we, with the new Lagrangian, will yield equivalent equations of motions as to the standard Lagrangian that we are usually working with. Now, for simplicity, we will just assume free fields for now. We will generalize that later. And the Lorentz condition of lambda equal to 0 can just be written in terms of the vector potential and the scalar potential. And using the expansion in terms of normal variables, that is nothing else than AL minus AS, so the longitudinal minus the scalar normal variable equal to 0. And this, on the other hand, suggests then that we define new variables, AD and AG, which are just linear combinations of the old variables, where AD is 0 under the Lorentz condition and AG is remaining. So remember that we had also a gauge degree of freedom, or some gauge degrees of freedom left, that was associated with F, which had to satisfy the box of F equal to 0. Now, if we do this, if we implement F, then we see that all normal variables will stay the same, except for alpha G. And so our gauge degrees of freedom is solely attributed to the change in alpha G. And we can write this in terms of effectively also the normal variables of F, just as we did with the scalar and the vector potential before. And so we can now, after gauge transformation, relate old and new alpha G. So a couple of things need to be mentioned now. So in any given Lorentz frame, obviously we can just choose that alpha G equal to 0. And that is also then concurring what we did in our non-relativistic treatment of atoms, that we also only found that there are 2 photon polarizations that of course are just associated with the transverse directions transverse with respect to the wave vector of the field nodes. However, if we are now interested in changes of reference frame and Lorentz transformation and in a covariant treatment, this does not hold any longer. And therefore, for very general terms, we cannot just assume that this is zero. And therefore, we want to first retain a scalar potential and more generally, the other photon polarizations. Okay, so now we want to write the field operators. Well, they're not quite operators yet, but on the way to after quantization. So we can write f. Remember, f was basically the generalized Fourier transform of small f. And if we make this choice for f, so that it also satisfies the box of small f equal to 0, and we then decompose our four potential in terms of the transverse degrees of freedom, the degrees of freedom associated with G and with D, we can write then our different components of the vector potential, the four vector as usual here, where we just have the transverse degrees of freedom that is very familiar from our standard non-relativistic approach. The gauge degrees of freedom are solely here associated with the scalar function f. And under the Lorentz condition, we know that for any physical field states, we have no contribution from the polarization associated with D. Now, however, as we are interested in observable, measurable things, we have to look at, for instance, the electric and the magnetic field. And just by definition, one can show then, due to the antisymmetry, that is purely transverse and only the transverse components of the four potential survive. And that's exactly as we would hope for. Now, we can write the Hamiltonians in terms of these new variables. And we see now that under imposing the Lorentz condition, that is alpha d equal to 0, these terms vanish, and we just have something that we are used to from our standard approach. And that means under the Lorentz condition, the energy of the free fields in this case have, and therefore the physical states have no negative energies. And that's exactly as we wanted. All right. So now we can do quantization after we understood a bit in more detail the physical implications of including redundant degrees of freedom. And in principle, we could do now direct quantization, which is a very nice and general approach. But this goes beyond what I want to talk about here. Unfortunately, it's definitely a topic on its own that should be discussed. But it's more a heuristically treatment that we do now for relativistic QED. So first of all, let's talk about canonical quantization. So what we could do now is we impose canonical equal time commutation relations, and then going to the Heisenberg picture in real space, we see that the commutation relation between the four potential is manifestly covariant. That is, we have some propagator, and we have here the Minkowski metric. We could then promote our normal variables to creation and annihilation operators. And just to be precise, these are not four vectors, it's just for convenience. They're sorted together. And they also have the metric associated with Minkowski, that is 1 minus and 3 plus. Now, the Lorentz condition in quantum theory cannot just be easily imposed. So that would amount to that the four divergence equal to 0. But the degrees of freedom associated with the longitudinal and the scalar polarizations are associated with different subspaces, and therefore identifying this as an operator identity is not possible. So in principle, we could now say instead that the average for any physical state psi has to be 0 for all space-time points, but this is not necessarily a vector space. And here, instead, to keep it more simple, we say that the positive frequency components acting on any physical states for any space-time point has to be 0. And what this implies is that the longitudinal annihilation operator minus the scalar annihilation operator acting on any physical state has to be 0 for all wave vectors k in our physical states. And from here, we could now construct the Fock space, starting from the usual vacuum state by defining that all annihilation operators acting on this yield 0. But we will see that there are some issues associated with that. First of all, let's define if one scalar photon state, that is, we have a creation of one scalar photon with a wave vector k, and we have some spread over k. We can show now that the norm is precisely minus the norm of the vacuum state times some non-zero coefficient. But this means that the vacuum and the one scalar photon have norms with opposite sign, and therefore we cannot have a probabilistic interpretation of our theory here. And so what it eventually means, ultimately means, is that canonical quantization fails. And there are different ways to approach this. And what we will discuss now is that we generalize the notion of norm in the state space, and it is associated then with the Gupta-Bloiler formalism, and we will see how this remedies the pathologies that we just encountered. So what we will do now is covariant quantization with an indefinite metric. So that means we will introduce a second scalar product on the same Hilbert space. We will define new adjoints and therefore also new mean values for operators, and then quantize with the new Hermitian conjugates. All right. So let's look at first at the standard inner product. So we know that we have a positive definite norm associated with a standard inner product, and we can now define a Hermitian and a unitary linear operator capital M that is not specified for now. And with this operator, we define a second scalar product that is now associated with standard brackets in the following form, that bra phi m cat psi is our new inner product. And so we can identify, oh sorry, this should be also a round bracket. We can identify the new state with the old state, and the new cat with the old cat, and the new bra with the old bra times the M operator. And now what we see, that this new inner product is of course not necessarily positive definite. So if you write this in this form, then we can see that the eigenvalues can be plus or minus 1. And so there is of course not a positive definite norm necessary. And so in general, we also don't have in general probabilistic interpretation. But first, let's talk about the new adjoints. So we can define in the same way as usual new adjoints in this relation. And looking at the left side and the right side separately, we can see that is what this implies as a relation between new and old adjoints. So the left-hand side can be written in this form. We just have MA, and the right-hand side can be written in this form, MA, but then we have the conjugate. And so we write this then with the old adjoints associated with the dagger. Equating both equation 28 and 29, we see now that the old and the new adjoints are just equal up to conjugation by M. And if we say that A is Hermitian with respect to the second inner product, then we have this, of course, the standard expression. And so we can also then define a new mean value just in the same way as before. And if A is adjoint with respect to the second inner product, then this will be real. Okay, so let's talk a little bit more about the implications. So as I said, even if we have Hermitian operators, there's generally no probabilistic interpretation just due to the indefiniteness of our M operator. But we are interested for now here in the gauge-dependent potential operators A mu that not necessarily are our physical observables. And so what we will do now is we will drop the usual hermeticity requirement with respect to the old inner product and require instead hermeticity with respect to the new inner product. So this is necessary so that we can ensure that the mean values of our equation of motions coincide with classical solutions. But what is important then is that we make sure that under this new definition, we still have that our physical observables check out as we observed before and as we are used to. And now the question is, what do we choose for M? Again, what we require now is that with respect to the second inner product, our operators for potential is Hermitian, and we do the same for the canonical conjugate. Then we do basically the same work as before. So we expand our operators in terms of creation and annihilation operators that are just defined now with respect to this second adjoint. And they have the same canonical commutation relation as before, where we have a minus sign associated with the scalar potential. And so what we will choose for M now is, of course, we saw that our transverse component or transverse polarization of the photon field are exactly as one would hope for. So we want that A associated with the spatial index and M commute, and that the scalar degrees of freedom anti-commutes with M. And so we can then relate our new adjoint with the old adjoint via a minus sign. And what this lets us do is that the canonical commutation relation associated with the old operators, that is the old adjoint, flips in its sign and becomes a standard plus sign. And if you write our Hamiltonian now in terms of these operators associated with the first inner product and therefore with the old dagger adjoints, we see that the Hamiltonian has a non-negative spectrum. And of course, the eigenvalues of an operator are independent of its metric. And so that is exactly what we want. What we see now, of course, through this choice of M, is that our scalar potential, that is U, AS, with respect to the old norm is anti-Hermitian. But this is not really a problem, since this is not an observable that we're interested anyway. In the end, we are interested in electric and magnetic field operators. So how do we construct M? And one can show that by imposing how M acts on Fock states associated with the scalar polarizations or time-lag polarizations, that it just adds a phase to these states. Okay, so how do we define now physical states? So let's go back to our diagonal operators AD and AG that were just linear combinations of the longitudinal and the time-lag polarization. And our Lorentz condition becomes simply then that the AD annihilation operator acting on any physical state for any wave vector has to be 0. And from then we can construct the Fock basis, where of course now the excitations in D have to be 0. And just in the usual form, we can write our Fock basis. And with respect to the new inner product, we can then show that the basis vectors are 0 unless the excitations in the G modes are for both basis vectors 0. And so if we look for any physical state that we can write now as our physical state associated with the transverse degrees of freedom, some tensor product sum some excitations in G and the vacuum in D, that the new inner product equals the old inner product times some coefficient. And of course, that's nothing else than the gauge degrees of freedom that we discussed before, and that in the Gupta-Bloiler formalism, we have to look at the quotient space because of the gauge degrees of freedom. And after quotienting out the gauge degrees of freedom, we are just left with the usual transverse polarizations. Let's look now at expectation values and what we did before. So we decomposed our 4 potential in terms of the transverse, the G components, and the D components. And we want to see what, for any physical state now, the mean values are. So one can show that the mean value with respect to the second inner norm equals the inner product with respect equals the mean value with respect to the old inner norm associated with the transverse degrees of freedom, plus some gauge freedom here. And so again, let me clarify or say again that the gauge arbitrariness is solely in the number of excitations associated with the G modes. And if you look just at physical observables, in particular the electromagnetic field strength tensor, then those remain unchanged with respect to the old and the new inner product, so that they are only dependent on the transverse polarizations. And indeed, also the Hamiltonian can be written in the same form that the new Hamiltonian with respect, the mean value with respect to the second inner norm is just the old mean value associated with the transverse degrees of freedom. And that is exactly as we would hope for. All right, so what we've done so far was just considering free fields, and what was rather that simplified things considerably, but showed us that we cannot just use a standard canonical quantization approach, but we have to use something else. In this context, we worked with the second inner product. Now we want to look at what happens if we interact with matter in order to describe eventually how do we interact with atoms and how we can relate that to our non-relativistic prescription. So first of all, let's say we have we have our Dirac field in order to describe fermions, could be electron or positrons in this case. And I just show you here without a derivation that the second quantized Dirac field has the following Hamiltonian associated with the particles and antiparticles, and the spectrum according with the rest mass and the momentum. So now we can then also, as usual, describe the interaction between the Maxwell and the Dirac fields. And it's nothing else than our minimal coupling prescription, where the charge current, the 4 current associated with the Dirac field, is just now accordingly equated with the Dirac fields. So what becomes of the Lorentz condition if we have interaction with matter? So in the quantum case, we had to impose that, for instance, the expectation value has to be 0 of the 4 divergence. And this means that we no longer have just AD, that means AL minus AS, acting on any physical state to be 0, but we also have another term that comes exactly from the charge density associated with our matter fields. And that is what we write here as lambda. And this makes things more complicated, of course, since we cannot just say that the degrees of freedom associated with the depolarization equal to 0. So our purpose now is to find the non-relativistic Coulomb Hamiltonian to relate now the relativistic covariant formulation with our old treatment. In order to do this, let us now decompose our full field matter system and the Hamiltonian in terms of the different degrees of freedom of electromagnetism. That was the transverse, the longitudinal, and the scalar degrees of freedom. So first of all, we have the Dirac Hamiltonian, then the free contributions according to the different degrees of freedom, and then the interaction similarly. What we can do now is we just look at first at the scalar contribution to the free field in the interaction Hamiltonian. And one can show you can write it in terms of course, the scalar creation and annihilation operators with respect to the second inner product, and lambda, which I remind you again, is the associated with the charge current at the charge density of the Dirac matter fields. And we can rewrite this in the following form, where we just have the adjoint minus lambda star and times as minus lambda. And so this will be now a very useful form for us, because we want to find now a unitary transformation to go to the Coulomb gauge. So first of all, what we can see is that lambda star and lambda commute with the scalar operators, because they are just dependent on the scalar, the charge density, but they also commute amongst themselves. And so what we see then, that the commutation relations can be written in the following form. And this suggests that we can find a translation operator T such that the conjugation of as minus lambda gives us as, and the same for the adjoint expression. And indeed, we can show that this is satisfied by the following operator, where we have the exponentiation of lambda a bar minus lambda star as. And with respect to the second inner product, indeed, T is a unitary operator. And so that allows us to perform now a canonical transformation to a different representation of our relativistic light matter Hamiltonian. But first we have to see what is the implications of this conjugation, canonical transformation on our first part of the Hamiltonian that we consider, that is the scalar degrees of freedom for the free field and the interaction Hamiltonian contribution. And so after this transformation, this is just the usual free field contribution plus another term, and recalling that we can write lambda in terms of the charge density, we see that the second term is nothing else but the Coulomb interaction between our matter content. So what it means is that our transformed scalar potential is the old potential plus the potential generated by our charges. And of course, that is something that is very familiar from our non-relativistic treatment, where we have the separation, which is very valid at low energies, of the Coulomb potential from the rest of the interaction. Now we need to check what happens if you do the canonical transformation on the other parts of the Hamiltonian. And you can see that the only other part of the Hamiltonian is affected by is the Dirac Hamiltonian. And so Dirac Hamiltonian after conjugation is equal to the old Dirac Hamiltonian plus an interaction between the scalar and the longitudinal degrees of freedom of the field. And you can write this in the following form, where S is defined in this form, is basically part of the generator of our canonical transformation. And so it allows us to write the interaction part in the following form. So the only interaction that is associated with the longitudinal and the scalar degrees of freedom now becomes the following, that we have the longitudinal component of the vector potential minus the gradient of S. And this can be solely written in terms of the creation and annihilation operators associated with D. And so this is very important, because now the interaction of scalar and longitudinal degrees of freedom can be completely written just in terms of creation and annihilation operators of D. Because recall also that we had the Lorentz condition, and the Lorentz condition under matter interaction had the following form. But now we have to also imply the transformation to this Lorentz condition. And what it means now is that this is nothing else after transformation, but the free field condition, where the new state can be written in terms of the old state with the action of the unitary operator. And so after canonical transformation, to be explicit, the interaction term containing our degrees of freedom associated with D do not contribute to transition probabilities. And so it's perfectly clear and fine that we just start any initial state without losing any of our generality with a vacuum in the longitudinal and the scalar, i.e. the temporal polarization. And therefore, after interaction, this will also be still in the vacuum. And so we can just drop the interaction with the longitudinal and the scalar degrees of freedom. And the full Hamiltonian is in the following form. We have the particle content, and this is just a particular representation of our Dirac Hamiltonian that will be very suitable for what follows, plus the Coulomb interaction. We have the standard free field contribution that is just associated with the transverse degrees of freedom, and we have the interaction associated with the transverse degrees of freedom coupling to the matter minimally. And alpha is just here related to the usual Dirac matrices, the spatial components of those. And the claim now is that this Hamiltonian is nothing else than a relativistic quantum electrodynamical Hamiltonian in the Coulomb gauge. And so what we have to show now is if we do the appropriate limit, that this of course then reduces to our Hamiltonian that we had in the very first lecture, and it we also worked in the second lecture, and what is essentially the basis for many quantum optical models. So the non-relativistic limit, how do we find that? What we're going to do is that we have now perturbations around our Hamiltonian, what we call H0. So that was just this contribution here as our basis Hamiltonian. And we need to find now perturbations according to V, which come from the Coulomb potential, the free field Hamiltonian, and H1, where H1 composes of the interaction part and also the part of the Dirac Hamiltonian. And now what we see here, of course, is because there's a factor of C that we have to go to one order higher if we want to compare it to the other parts of our perturbation. And in the end, what we want to find is the leading order perturbation. So we start with the expansion of the matter field in the following form, where we have C and B are associated with the creation and annihilation operators of particles and antiparticles. And we have an expansion in terms of a spinor basis, where those are eigenfunctions to the corresponding H0. They are also eigenfunctions to the momentum operator and to Pauli Z operator. And so they are not the usual spinor basis that we would use for the full Dirac Hamiltonian, just because we're doing perturbation theory now. And those are associated with corresponding momentum and spin sigma. And so after this expansion, we can recast our H0 in terms of constant contribution and in terms of this form. So these operators just have eigenvalues 0 or 1. And so for each momentum and for each spin, we have a discrete number of excitations, at most 1, and those are just then the rest masses associated with each excitation of particles and antiparticles. And again, the most important part, the most complicated part will be to find the perturbation due to H1. So that was the contribution that come from part of the Dirac Hamiltonian and part of the interaction with the transverse degrees of freedom of the field. And one can show that you can write it in terms of contribution coming from the particle content, which I denote here as the electronic content, and the antiparticle content, which will be positrons. And as we will in the end just be interested in electrons or particles, I'm just going to give you the first expression. And you see this seems also already very familiar, but of course a bit more complicated still, because we have creation and annihilation operators for excitations of electrons. Okay, so now let's say we only want to consider electronic states, and we put everything together. So first of all, we just have the rest masses associated with how many electronic excitations we have. We have then the Coulomb interaction, where this is nothing else than the charge density written in suitable form. We have the free transverse Hamiltonian contribution, the free field, and we have still this part here that came from delta E. Now what we assume now is that we have initially and in the final state the same number of electrons, and we take then the matrix element associated with that. What we find is then that we have a constant contribution coming from how many excitations, how many electrons now, since we are in a non-relativistic regime. So it means how many fixed number of electrons do we have, and of course that can be neglected. What we then have from this contribution is the usual minimal coupling part, where we have P minus QA, where just A is of course the transverse vector potential. We have then the Coulomb field, and we have the free Hamiltonian associated with transverse degrees of freedom. But of course, since we now initially considered fermions, we also have the Pauli contribution, where we have the spin of the electron coupling to the magnetic field, where this is usually subleading order and we neglect it. And this is exactly what we were looking for. So now we have the justification of our usual minimal coupling Hamiltonian to leading order coming from our covariant formulation. And of course, if we were now interested to higher leading orders, that means to 1 over C, we would find correction terms, and that would give us the bright Hamiltonian, which would include this spin orbit coupling, Zitterbewegung, and so forth. Okay, so let me conclude. So what we saw was how we can find a covariant formulation of QED that necessitated us to not have a standard canonical transformation, but we had to do a couple of tricks that were related to finding a new norm and a new inner product and a new adjoint operators. We showed then how we can implement interaction with matter fields. And then most importantly, we showed how this, after canonical transformation, gives us a relativistic Hamiltonian of the interaction between light and matter in the Coulomb gauge. And after the low energy limit in the leading order, we found that we can derive the non-relativistic multiple minimal coupling Hamiltonian in the Coulomb gauge. And it's our justification of why we can write this Hamiltonian, where we explicitly separated the Coulomb interaction from the rest of our Hamiltonian, of our interaction between light and matter. Okay, and with that, I want to conclude and invite you for questions.
All right, thank you, Richard. Any questions? All right, well, if there are any questions, let's thank Richard for the seminar. Thank you, Richard, for the seminar and for the whole series of seminars. They were great, very instructive.